Okay, I think we can start our today's lecture on artificial neural networks. In our previous lecture, we have started discussion on ANN, artificial neural networks. Am I clearly audible? Okay. So we have started our discussion on it. That is ANN, and in our last class we have discussed about that is the basic definition of artificial neural networks, and then how to form a neural network. And then what's the similarity between our artificial neural networks and biological neural networks? And then we have discussed how to form the classification problem in neural networks and also the regression problem in neural networks. And then we started discussion on neural network training. Specifically, we finished the first part, that is the forward propagation part. And we know that the forward propagation is for the prediction, okay? That means um, based on the assigned weights and the input, we have to predict the output. So the forward propagation is for predicting the output. And then based on the prediction, if there is any error, then it will try to update the weights of the neural networks. That is called our. And then after updating the weights, it will try to that is predict the perfect score or perfectly. Like it can be a classification problem, or it can be a regression problem, but we need to predict the class correctly, or we need to correct the value for the regression value correctly. Okay, so using the back propagation, it will try to update the weights of the neural networks so that it can predict the either the regression values or the classification classes correctly. So we have discussed this, that is the forward propagation, steps of forward propagation. And we have discussed also that there is the activation function, specifically the sigmoid function, okay? The structure of the sigmoid. And based on the sigmoid, we have assigned few initial values. And based on those initial values, we have calculated the error. Okay, we have calculated the error, and we can see. Okay, so we have started one example, and on that example of the neural network, we have assigned the weights, that is the W1 to W9. These are weights randomly. We have assigned the weights randomly. This is the initialization. Okay, initially we have assigned these weights, and then we assume one data set, and then that data set, actually we have the two features, like one feature 1 and feature 2, and the output is this. Uh, and for this, we consider the output, this one, the first output. Okay, so the first input. So this x1 is 1 and x2 is also 1. X1 is 1 and x2 is also 1. Then we expect the output 0. Okay, output 0 here. This is our expectation, and we assigned the weight initially. So these are the random assignments within 0 to 1. So all the weights we have assigned within 0 to 1. And then we have performed the forward propagation. We have performed the forward propagation here. We have discussed those things in our last class. And then finally, you can see that the predicted weight or predicted value here, Based on our assigned weight, it is 0.774. 0.774. Okay, 0.774. And then we have started the back propagation based on the error, because we need to minimize the error. Okay, minimize the error. So for error minimization, what we have just, these are the words, so we need to update the words, these words and these words. And we will start the hidden to output layer words. So hidden to output layer words, at first we need to actually update these words, and then hidden to hidden, and maybe input to hidden. Here is the input to hidden layer. Okay, that means these words. So firstly we need to update the hidden to output, and then input to hidden. So in this backward direction. So that's why it is called back propagation. That means propagating the errors in backward way or backward manner. And for that, here for backward propagation, we have started this session also. At first, we need to calculate the output sum margin error. That is, error here is target minus calculated. Our target is 0, and the calculated value or predicted value or result we got, the result is 0.77. So target minus calculated, it is negative 0.77. And then if this is the error, then actually this value or predicted value or calculated value, this value, it is depends on, firstly depends on the sigmoid. Okay, because in our forward propagation, in the last layer, what we did this, that is sigmoid of the sum. So sigmoid of the sum, this is our last operation. Okay, last operation performed in our forward propagation. So that means we have to start from here. We have to start from here to update our calculated values, to update the weights of our hidden to output layer weights. Okay, so that means we have to start from here. That means we have to determine that how much change we need to adjust, how much change we need to do if we want to change the calculated value. Okay, or you can say predicted value. So on that case, what we have to do, we have to take the derivative of the sigmoid of the sum with respect to our calculated value. Then we will get that. Okay, so we have started here. That is, this is the last layer operation we have performed, like is sigmoid of the sum equal result or predicted value. Now, if we take the derivative, so we can see that there is rate of change of this. This is equivalent to d sum by d result, and then our the error here is, there is, if we take the derivative of that, then this is called the delta sum. Okay, delta sum. So this delta sum, we calculated the delta sum, and one property of our sigmoid function, that is, we have to take the derivative of this sigmoid. Okay, so one property of the derivative of the sigmoid we have discussed in our last class. That is, this is the sigmoid function. If we take the derivative of the sigmoid, it will be, that is, if we want to find out the derivative of a sigmoid, so it will be the sigmoid of that function, sigmoid of that value, that is sigmoid of x, then 1 minus sigmoid of the x, sigmoid of the x. So that is, it is a nice property, that because if we calculate only the sigmoid of the x, then we can easily find also the derivative of the sigmoid of the x. Okay, so now here for our example, we want to find out the delta output sum. Okay, delta output sum, and on that case we can see that the derivative of the sigmoid of the sum and output sum margin error. Okay, so this is our delta output sum. So from this equation, okay, from this equation, delta output sum. So it is derivative of the sigma of the sum, because d sum by d, the result is what? It is derivative of the sigma of the sum. And here is the target result minus calculated result. This is our error. And then we will get delta output sum, delta of the output units of summation. Okay, so here derivative of the sigma of the sum times margin error. We know the margin error is this, and then sigma of the sum. So derivative of the sigma of the sum. What's the value of the sum in our case? In our forward propagation, we have already calculated the sum, or you can say here this is the sum. Okay, the sum. The value of the sum is 1.235. 1.235. And derivative of the sigma, derivative sigma of the sum, we have calculated it is 0.774. 0.774. So what we have to do there, uh, here we can see, uh, we need to find out derivative of the sigma of the sum. Sum we have already calculated, so that is 1.235. Now if we want to calculate this, that is derivative of the sigma of the sum, it will be the sigma of the sum, sigma of the sum, sigma of the 1.235 times 1 minus sigma of 1.235. Okay, this one. So we have already calculated the sigma of this sum, and that is 0.774. Okay, 774. So it will be 0.774 times 1 minus 0.774. So if we put those values here, then we will get this, that is times minus of 0.77, then we will get this. Okay? So this is our delta output sum, or sometimes we call delta sum, delta sum, or sometimes we call there is delta output sum, output sum. Okay, so we already got that, that is the delta output sum, we determined that. But now what we have to do, we want to update these values, at first update these values, but whether we need to change it positively or negatively. That means whether we need to increase the value of 0.3, 0.5 or 0.9, or we need to decrease the value of 0.3, 0.5 and 0.9. It means that we want to find out the delta, we want to find out the delta, we need to find out delta weights hidden to output layers. Okay, so we need to find out this one. So if we find out this value, then we can see that there is uh, by adding this value delta WHO to our existing W, we will get, that is what will be our next consideration. But again, this delta, it must be associated with our, there is the current output sum. Okay, there is delta output sum. So that's why one equation here, this is the equation. This is equation, actually we followed this equation for calculating our forward propagation. Okay, there is H results times W equal output sum. So we wrote that here in vector form. So here hidden layer results time weight equal output sum. Yeah, that's actually we have calculated already in our forward propagation. In our forward propagation, we can see here there is sigma of h1, and here the sigma of h2 and sigma of h3. These three sigma values we have multiplied with W7, W8 and W9. Okay, to get this sum. So this is our output sum. Okay, output sum. So it means that if we consider that the segment of A, segment of H2 and segment of H3 as the hidden layer results. So hidden layer values and hidden layer, here is the hidden results. So H results, this is equal our sigmoid of H1, sigmoid of H2, and sigmoid of H3. H3. Okay, so this is our H results. And then the weights, these are the weights. So these weights W7, W8, and W9. If we consider that these are the weights of hidden to output units, vector. So that is W7, W8, and W9 vector. Then actually here this equation, we can form this equation actually using the multiplication of these two vectors. There is H results and WHO. Okay, so first one it will be sigma H1, and here is W7, and then sigma of H2 it will be W8, then sigma of H3 times W9. Okay, so and it will produce what? It will produce the sum, or you can say output sum. Okay, output sum, because it will produce the sum of the output unit. Okay, that's why uh, this equation actually we have used in forward propagation. H results times W equal output sum. And from that equation, you can see here, this is the equation we have already used in forward propagation. From this equation, if we take the derivative of this with respect to W, with respect to W, so it will be in this side, it will be H results equal yeah, because we can say WHO, we are taking the derivative with respect to that, so it will be 1. So H results time 1. Okay, so it will be like H results time 1 equal delta output sum, delta O sum by delta delta of WHO. So we will get this. In this case, we can see that is H results equal delta O sum by delta HO. Now we want to find out this, that is delta WHO. So that's what we are actually uh, searching for here. So delta WHO. So it will be our delta O sum, whatever the value we got in delta O sum, divided by H results. Divided by H results. So we can say delta output sum by delta H results. But we have already calculated the delta output sum, and this is the delta output sum. Okay, we can see this is the delta output sum. It is negative 0.134. So here it is. Here you can say delta output sum negative 0.134 divided by here hidden layer results. Okay, so hidden layer results, we know the hidden layer results from our forward propagation. We already calculated the what are the hidden layer results. Hidden layer results actually we assume that, what is that, So here the hidden layer results is the sigma of H1, sigma of H2, and sigma of H3. So 73, sigma of H2 is 0.79, and sigma of H3 is 0.69. Okay, so we have already calculated those values. That means we can use those values from the forward propagation. So from the forward propagation, we have used those values. And now we can see delta weights. It will be this one divided by this value, and similarly this one divided by this value, and this one divided by this value. So we will get what? We will get these values. So these are our delta weights. So delta weights, that means we can see that delta of delta W of hidden to output units, we have three elements here. This one is our W7, W8, and W9, and we can see W7 will updated by this value, W8 will update by this value, and W9 will update by this value. So how can we compute that? So here these are the W7, W8, and W9, and previous words, that is these are the values of the previous words plus of delta words. So delta words, we know the value of the delta words. Then we will get the new values. These are the new values. New W7, new W8, and new W9. Okay, so we will get these new values. It means that previously we have 0.3, 0.5, and 0.9, but currently in next iteration we have to use these values: 0.1162, 0.329, and 0.708. We have to use these values. Okay, now we can see that we have updated the weights of hidden to output units, only, that is this value. But still we need to find out the way to update these values. Okay, update these values, and for that we have to do a little more. At first, we can use the same equation. That means this equation we have already have taken the derivative with respect to W, but this time we want to take the derivative of this same equation with respect to output sum. Okay, so if we take the derivative of this equation with respect to output sum, then it will be delta hidden results. So here is the delta hidden results by output sum, and here is the WHO. Okay, so it means uh, from here, if we take the derivative with respect to delta output sum, then it will be delta hidden results sorry, so delta hidden results by delta output sum times this one, that is the WHO equal, we are taking the derivative with respect to delta output sum, so this time it will be 1. Then we will get like delta hidden results divided by delta output sum equal 1 by WHO. So 1 by WHO. From here we can find out here there is delta hidden results. This value, it is the delta hidden results, hidden layer results times WHO equal our delta O sum. And then from here we can write delta hidden results equal delta O sum divided by WHO hidden to output layers. Okay, that means delta of hidden results, that is rate of change of hidden layer results. Here rate of change of hidden layer results, these are the hidden layer results. Hidden layer results, it will depend on delta output sum. So delta output sum, we already determined the delta output sum if we divide it by WHO. Okay, so here the delta hidden results, it will be delta output sum by this one. Okay, now so this is just we can consider this one is the equation number 1 or something. Okay, equation number 1. Now we have one equation already. We have one equation that is previously we have used here, this one. Sigmoid of the sum equal result. Okay, we applied sigmoid to output layer, but we also applied the sigmoid to hidden layer. Okay, so for the output layer, this is actually we can write this is the sigmoid of the sum. Okay, sum, you can say output sum. Here the output sum, there is output layer summation, it is equal our results. Okay, so instead of the output sum, we also applied the sigmoid function in our hidden units also. So on that case, if we apply that, that is the same thing. It means that we applied this sigmoid in hidden sum. There is summation of in hidden layer, hidden sum is actually our hidden results. Okay, hidden layer results. Okay, so that means what we did, we applied the sigmoid in our hidden sum and we got the hidden result. That's what we have done actually uh, in our forward propagation. Okay, that means the summation we got, this is the summation, the hidden layer summation 1. Here is, this is the hidden layer summation, there is 1.3 and 0.8. So we got this, that is the h1, h2 and h3. Okay, and then we apply the sigmoid of h1 to get our hidden layer result. So to get these values, get these values, get these values. So that's the same. So that's what we are trying to write here. That is sigmoid of the hidden layer sum equal hidden results. Again, if we take the derivative of it, that means we can say derivative of the sigmoid of hidden layers summation. It is what? It is our dA sum. So it will be our delta A sum. So delta A sum by delta A's results. That is the similar case like here. Similar case. Similarly. So that's what it is written in this equation now. You can see that uh, derivative of the sigmoid of the sum, it is delta hidden sum by delta hidden results. Yeah, we know this. We know this. Okay, we know this. And now both side of equation 1, this is our equation 1. Okay, this is our equation 1. So uh, if we just multiply both side of this equation using this one, using this value. So here we can say dA sum by dA result. That means this left hand side we have to multiply with dA sum by dA result. dA sum by dA result. And this side also, okay, this side you have to multiply with the dA sum and dA result. Okay. So now we can see here there is, this is the relationship. Okay, this is the relationship, and now we can see there is, here is the delta S result, and here is also delta S results. Okay, so directly we can write that here is the ds sum equal this part. So ds sum equal delta S sum equal delta output sum by WHO times delta S sum by delta H results. Actually, ds sum by ds results is what? This is our derivative of the sigmoid of hidden sum. Okay, so that's why we have written here. This is the derivative of the sigmoid of the hidden sum. So from this one, we can write that, and this part, uh, that is this part, we have written delta was output sum by WHO equal delta H sum. So here is the delta H sum. So that means delta H sum equal delta output sum divided by WHO times derivative of the sigmoid of hidden sum. So using this equation, we can find out, delta hidden sum, delta of hidden sum. So that means delta of hidden sum, this is the hidden sum, this is the hidden sum, and this is the hidden sum. We can find out that is rate of change of our hidden sum. Okay, so this is called delta hidden sum. Here is this, there is derivative of the sigmoid of the hidden sum. So we can apply this one to find out the delta hidden sum. Delta hidden sum. Okay, so that means delta hidden sum, we already got the delta hidden sum, but that is not the target. Target is to find out our delta of input to hidden layer weights. So actually we need to find out W of input to hidden layer weights, the delta. That means rate of change of W. Okay, so currently we are getting here delta H sum. Okay, get delta H sum. At first we can determine the delta H sum. So here delta hidden sum, it is delta output sum divided by hidden to output layer weights and sigmoid of the hidden sum. So sigmoid of the hidden sum we have, that is the sigmoid of the hidden sum. So here is this is the hidden sum 1, and here is the 1.3 and 1.08. That means sigma of 1, sigma of 1.3 and sigma of 0.8. 0.8. So that means we already know these values. So this values is equivalent to like 0. This is the case. Okay, the 0.73. It is 0.73, and next one it is 0.79, 0.79, and then next one is 0.69. So it is 0.69. But what we need the derivative. Okay, derivative of the
Sir,
hello.
sir, are we updating the hidden sums also? Or are we just trying to update the weights from input to hidden?
Actually, we need to update this one. That is weight of input to hidden layer. Okay, this weight, this weights.
So
But
in doing that, are we updating the hiddens also?
we
Like
are
this
not
gives this
updating.
delta hidden.
We are calculating just. Actually,
Yes.
to update this one, we need that. Okay,
So we
that's
will
why we
get
are
a
calculating.
new hidden sum during
Yeah,
that
we
calculation.
the rate of change of hidden sum. If we want to update this one, we need to calculate the delta hidden sum, and that's what we are doing. Okay, there is a relationship between our delta W input to hidden, this one, and our delta hidden sum. Okay, we will build that build a relation between these two. So that's what we are currently updating this one using these equations, and we using these derivations actually we got that relationship. You understand?
Yes, sir.
Okay, so currently we are updating, not the updating, we are calculating. Actually, no need to update because only we need to update the weights. But to update the weights, we need to calculate something more. Okay, and that's what we are calculating. So here using this relation, and this is the valid relation because we can see that already we got this relation from our equations, that is from our the equations and derivatives. So that's what we are using here. So now delta output sum, we already know the delta output sum and also the sigmoid. So here the sigmoid of 1, sigmoid of 1.3, sigmoid of 0.8. So a sigmoid of 1 is what? Sigmoid of 1 is 0.73 times 1 minus 0.73. So we will get the sigmoid value, and then sigmoid of 1.3, it will be 1 minus 0.79, and 0.8 it is 0. This value times 1 minus 0.69. Okay, so then we will get the sigma. So that is the derivative of sigma of the hidden sum. So here is the derivative of the sigma of the hidden sum, and on that case we will get we will get this value. Okay, so that means 0. It is equivalent to like this one, 0.1966. Okay, 0.1966. Similarly, for this value, you will get 0.1683, and for last value, you will get 0.2193. Okay, 2193. Now, what we have to do? So we already got this value, and now here is delta output sum hidden to output layer weights. So delta hidden sum and delta hidden sum divided by hidden to output layer weights. So we know the hidden to output layer weights. What are the hidden to output layer weights? These are the weights. Okay, these are the weights: 0.3, 0.5, and 0.9. We have 0.3, 0.5, and 0.9. One thing you need to remember here, that is, we should not use the updated weights at this stage. So updated weights only used for the next iteration. We have already updated these weights. Okay, update these weights, but for this calculation we will not use the updated weights because we are updating weights for next iteration. So that's why whatever we have in our previous iteration, uh, these values we have to use here: 0.3, 0.5, and 0.9. And then after doing this we will get that, and we have already calculated this part, so this is that. So now if we multiply with these two, then we will get the hidden delta hidden sum. So delta hidden sum will be these values. These are the delta hidden sums. Okay, so we got the delta hidden sum, but that is not our target. Our target is to find out the update. That is the delta of input to hidden layer bars. That is, um, how can we change those values? Whether we need to increase the 0.8 to something, or we need to decrease 0.8 to something. Similarly for 0.4, whether we need to increase it or decrease it. If we increase, then how much we need to increase. If we decrease it, then how much. Okay, so we have at this stage delta hidden sum. There is delta hidden sum. We already calculated the delta hidden sum. But now we want to find a relationship between delta hidden sum and our that is delta of input to hidden layer. So for that, we have used this equation. This equation is what? This equation is already we used also in our forward propagation. So to calculate the hidden sum, we can say this is the hidden sum 1, 1.3, and 0.8. These are the hidden sum. To calculate the hidden sum, how we have calculated? We have calculated the like the H1. To calculate the H1, we have done like x1 times w1 plus of x2 times w5, like this one. So this is our h1. In this case we can see that actually this is the input and this is our weight of our input to hidden layer. So here is the input and this is our weight to input to hidden layer, and we got this hidden sum. Okay, we got this hidden sum. So we just write the same thing in vector form. Okay, in vector form, and now we can see here that is here the input and this one. So in this vector actually we have the input is our x1 and x2. Okay, x1 and x2. So transpose of that vector, and our w in this case we can see here the one is for this case for the hidden one we have w1 and w5. Sorry, is it w5, w1, w2, w3, w4? Okay, actually it is w4, so it is w4, and then w2, and we have w5, and w3, and we have w4, w4, w6. Okay, so this is our this is our w input to hidden vector for that, and this is our input vector, this is our I, this is our I. So that's what we have already find out this, that is the output will be this, output will be what, output is our hidden sum, that is hidden sum is our h1, h2 and h3. So this is the actual structure. So in our hidden sum, this is our hidden sum, it is equal the input and times our weight, that is weight of input to hidden layer. Okay, so this equation we used in our forward propagation. So that's this equation. And now what we have to do, now we can take the derivative of this equation with respect to w. If we take the derivative with respect to w, then it will be it will be for this side it will be just 1 I, that is input times, we are taking derivative with respect to w, then it will be 1 times so here is the d sum, that is delta a sum divided by our delta of w h I, sorry, I h, input to hidden. So in this case you can see that is from here we can write delta w I h input to hidden layer, it will be our delta hidden sum divided by just the input. So this is the equation. Okay, so we already got what, we already got delta hidden sum in our previous calculations, and then we have to divide that one by our input, then we will get delta w I h. Okay, so now we can calculate it here. So delta hidden sum, we have already calculated delta hidden sum. Then divide, we have to, and this is our input 1 and 1, so we can say for the one we will get this, and for another one we will get that. So this is our delta weights. Okay, delta weights. So that means we got the delta weights, that means we can say this delta weight is our, we need to change these weights using our delta. So that means the old weights plus of delta weights. So if we do that, then these weights will be updated like this. So now these are the weights we have and the updated weights. So after first iteration, the forward propagation and backward propagation now complete. So what we have to do, we need to use these weights, that is updated weights, for our next iteration, and we have done that. So for the next iteration, we have used these weights, that is updated weights, and complete the forward propagation again for the same input like 1 and 1. And we can see here on that case the H1 is changed, H2 is also changed this time, and H3 is changed, and corresponding, that is the sigmoid, or we can say hidden layer results, is also changed. Here result changed. And finally we can see that there is the, this is our output sum and also the output results. Okay, output result, that is the predicted results or calculated result. It is 0.79, sorry, 0.69. So our target is 0 and this time we calculated the predicted value 0.69. So it is our second iteration. If we compare these values with our first iteration, so in our first iteration we have, it is 0, and the target and calculated value it is 0.774. 774. We can see that actually it is reducing towards the 0. So first value it was 0.774, but now it is 0.69. So error is reducing. Okay, that means just only one iteration is reducing. So if we perform like maybe 1000 iteration, then we will get 0. Okay, so this is how the neural network, the basic,
Sir, I have a question.
let's say,
Like,
basic
why are
neural
we using
network.
the same input again?
Same input again.
Why are we using the same one input? Should we like go for the other inputs that we have?
Yeah, we have to do for each, actually two kinds of system we have. One is called batch processing, one is called just uh, the, the single input. Okay, so that means one instance at a time. So we can see here there is the, we just put the same input. Okay, because we can see that is for this input you want 0. For other inputs, if we input like 00 or 10, like 01, your output is also changed. Output it will be like 1. The target is 1 on that case.
So, sir, until we get a zero or until we hit certain threshold, we will just continue using this one input.
Yeah, one input, and again we have to use the another one,
Yes,
that is
but
like
once we get
0.
the zero, then we move on to the other one.
Yeah, other one.
Sir, I
Okay.
have also like a very conceptual question. Like with regression, we were trying to fit a line with random forest which had some kind of impurity calculation and we did some kind of bagging to come to a result. But with neural networks, what exactly are we trying to draw, or are we drawing anything on a plane or something like that?
Yeah,
We're just
actually
looks
the
like we're just updating endless amounts of weights.
not exactly like this. It is also the same equation. That is, we can see that. So here the input, based on the input, based on your input, you want to predict something. Okay. So that means we can see that um, actually the equation is what? Equation is, in this case, in our case, we have like two features. Okay, f1 and f2. F1 and f2. Just to consider that this is a regression problem also. If we consider this, then based on the f1 and f2 values, we want to maybe predict something. Okay, so in this case, if we say about the regression problem, actually the same equation we want to find out, that is x1, the input, uh, or we can say f1 times w1 plus of f2 times w2. We have also bias, that is the plus b. So this is This is the regression line. Okay, this is the regression line, and actually here in neural network it is also doing the same. It will try to find out the w, these values, the w1 and w2. Okay, w1 w2, so that there is the optimal w and optimal w1 and optimal w2 will give us the optimal or best fitted line.
So this is for the hidden layer. Then we will do this again.
Not only the hidden layers, we can see here this layer and this layer. There's all the words, okay? All the words. So whatever the words there is, we can see W1, W2. We have many W's here, okay? And
So
here is
is
the
the
many
idea
W.
like we are doing multiple regressions?
The multiple regression, actually, we can see that the regression, if we have like just one independent feature and one dependent feature, usually we call that linear regression. And if we have multiple, there is a feature, then usually we call the multi regression. Actually, here is also doing the same multi regression, but
Okay.
usually we say
How?
the regression.
Right. Okay.
So that means these weights are the same as there is in neural networks. We are trying to find out the optimal weights. And in our linear regression, as we discussed in also gradient descent, one of the algorithm, gradient descent for finding out the optimal weights of the objective is the same. That means we have to find out the W, optimal W. So here I have discussed just only the sequential processing. That means we can say just one input sequence at a time. Next, I want to discuss about the batch processing. Okay. How can we apply the batch processing here? So you understand that is the fact here, the equation, because the same thing. Okay, we have the input and then the W. Usually the line is this. Okay. Uh, so what we do, W transpose X plus B. W transpose X plus B. So we want to find out the W. Using the linear regression, we want to find out the W like gradient descent. Here is also in neural networks, we want to find out this W. And I have already shown that the W means what? This is our W. Okay, so that means target is to find out the optimal values of W. Is it fine?
Yes, sir.
Okay, now I have applied the basic form of our neural network in this example, but I want to now upgrade a little. That means previously we didn't consider the bias, but now we have to think about the bias. Why we need to think about the bias? Because we know the equation. Okay, there is the W transpose X plus B. Yeah, this is the B. B is the bias. Okay, B is here in our linear regression. Usually we call the y-intercept. But for any equation, a constant is required. Okay, so that's why we have to think about the bias also. So now the concept of neural network, it will be a little bit, I can say, upgraded. So in our input layer, these are the input layers. And now hidden and output layers, we have to consider the bias. So here is the bias for each and every unit. So here is one bias, and here is one bias, and here is one bias. So this bias, this can be, we can say that this is our bias of hidden layers. So, this is our BH1, bias of hidden layer 1, and here is the bias of hidden layer, okay, of unit 2. So BH2, or you can say B1, B2. Here is the bias of output layer, the bias of output layer, okay. So we have to add these things. That means the equation will be, this time equation will be a little change. Like in our previous case, we have H1 forward propagation, X1 and W1 plus of X2 W4 So this was the equation previously, okay? But this time what we have to do, this one plus of b1, that is this value we have to add. Similarly for the h2 we have like x1 times w2 plus of x2 times w5 plus of, so there is our for the hidden layer 2, okay? So hidden layer 2 is p2. So in our previous equation we have three hidden layers, okay? Hidden 1, hidden 2, hidden 3. For each and every hidden layer we have to add the bias. So that means for h3, previously we have calculated like just x1 w3 plus of x2 w6, but this time we have to add the bias 3 in our third hidden layer unit. Similarly for the output, this is the output. In our output layer what we have done, so at first we have to find out that is the sigmoid of h1, sigmoid of h2, and sigmoid of h3. So it will be sigmoid of h1 times w7 plus of sigmoid of h2 times w8 plus of sigmoid of h3 times w9 plus of bias, that is bias of output layer, and this is our output sum or sum or output sum or sum output sum. And then the calculated value, for the calculated predicted value, what we have to do, just sigmoid of our output sum. Okay, so a little bit changed. This is our predicted value. Okay. Uh, so now in our second example, we will try to update the weights. That is using batch processing. So batch processing means we will not, that is taking the inputs just a sequential input, like maybe one. Previously we have shown that just input is 1 1. So now what we have to do, we have to think about our, so a little bit different way. We can see here the tabular method. So the step one, step 0, in this case we can see here there is a x. So x is 1 0 1 0 1 0 1 1 0 1 0 0. So consider that this is our now the input, and the output is here, that is 1 1 and 0. So it means that this is our first instance, that is instance number 1, instance number 1, and then this is the second instance, instance number 2, and this is the third instance, in instance number 3. So how many features here? How many features?
Four.
Yeah, we have 4 features here. So this is our feature 1, and then feature 2, and feature 3, and feature 4. Okay, so 4 features in this case. Now, instead of just maybe considering a single instance at a time, like previously, maybe you can say, uh, in our previous example, we have taken this as input, on input. But this time we want to apply the batch processing. That means we want to consider these inputs as a batch. base inputs. Then what will be our neural network steps? So at first we need to uh, our neural networks. Okay, so we can see how many features here. Four features. Okay, four features. That means the input in our neural networks, the input will be in our input layer. How many neurons we have to add? Four neurons we have to add because we have the four features. So here is the F1, then F2, then F3, and then F4. So four features we have to add. Four neurons we have to add. And now think about that is our hidden layers. Consider that just we will only use one hidden layer. Okay, one hidden layer. But how many neurons on that hidden layer? It will be user defined. And in this case, I assume that I have like three neurons in our hidden layer one. So this is our hidden layer one. We have three neurons in this case. So that means we can see here is the connection. Here is the connection. Here is the connection, and that connection. Okay, so we can see here that is we have in our h1. So here is the h1. We have to calculate the h1. We have to consider now four inputs. One from like x1, x2, x3, and x4. Four inputs. And for the hidden layer 2, it will also consider four inputs. Inputs from x1, input from x2, input from x3, and input from x4. Similarly, the last hidden layer here is there. It will also have input from x1, x2, x3, and x4. Okay, so we can see here that is in our in our hidden layer weights. So we have to assign weights for each and every edges. Like here you can see this is w1, w2 like this way. So here four neurons in our input layer and three neurons in our output layer. So in this case, we can see that is our dimension of our weight vector. That is dimension of our weight vector. This weight vector, it will be W. This weight vector will be what will be the dimension? So four inputs and three features. Three we can say hidden layers. It will be 4 by 3. Okay, 4 by 3. So here we can see here that is the WH, the the weight of the hidden layers. Okay, weight of the hidden layers. So these weights, it will be our like this. So four rows and three columns. Okay, three columns. So if we consider this neural network, and as I already mentioned that that means we have to consider the bias also. Okay, we have to consider the bias also. There is the bias of hidden layers. So but we have to consider the bias also. Okay, so that means we have to add the bias here and bias there and bias also there. So for that, what we have to do, the bias in this case, we can see uh, for each input, we have to consider also the bias. Okay, so here is this. That means this is our input, and then what just initialize with our WH. So here is this is our W. So W matrix. The W initially what we have to do, we have to assign just uh, any initial values with 0 to 1. So between 0 to 1 we have just assigned the words, and we have also the bias of hidden layers. The bias we can say we have 3 units, so 3 bias values. So this one and that one. Okay, so these bias values we have also initialized. Now what else we have in our network? We can see that we have already considered okay, let's say output is 1 or 0. Okay, let's say in our output unit we have just only one output neuron. We have to connect here like this. This is the way of connection. So in this case the output, the weight of the outputs, like W of output, W, so 3 outputs, and also we have to consider the bias of output. Okay, bias of output layer on value. So totally this output here, the weight of the output layer is also here, you can say initializing this just 3 values, and bias of output is also initialized. So this is the initialization. We have done the initialization first. Okay, so initialization, that means input and then weight and then bias, there is bias of units, and then weights of the output unit, and also weight of bias of the output unit. So these are just initialization. So is there any questions up to this slide? We have to understand the architecture first to understand the best process. Okay, I think no question from your side. Now what we have to do, the next thing is, for the batch processing we have to apply the same procedures we have used in our that is the sequential processing. Okay, sequential processing. It means that uh, we have to multiply this one with that one plus of this one to find out what, to find out our weights of to find out the hidden hidden layer values. Okay, hidden layer values. So for that what we have to do, we have to like the same thing, we have to multiply x and w and also plus of b, plus of b. Okay, so here is the x. You can see 1010 times this one. So we can say plus of this value 0.46. Then we will get the values. Okay, so here is, we can see uh, there is x 1 2 3 4, here is 1 2 3 4, and then plus of this, then we will get the hidden layer values. Okay, hidden layer values, and this one times that one, that is next, so we will get the next value, and this one times that one, we will get the next value, and then again for the second input we have to go the first column, then we will get this value, second column, then we will get this with this value, third column, then we will get this value. Okay, considering the third input, then again you can see we will get this value. Okay, so in this way we can find out the hidden layer inputs. So here we can see that is a matrix dot product of x and w. So x and w, if we multiply, and plus of bs will give us this value. So now we got the hidden layer inputs. Then what we have to do, we have to find out the sigmoid of each and every hidden layer values to find out hidden layer results or hidden layer activation. So that means sigmoid of 1.48, put this value here. Sigmoid of 1.78, put that value here like this. So we can see that After performing the sigmoid operation to the hidden layer, then we will get these values. Okay. So now the next thing is what? That in our forward propagation, the next thing is this is our hidden layer results. Then hidden layer results we have to multiply with the hidden layer weights. So here is the hidden layer weights plus of the our bias of output layer, bias of output layer to get what? To get the hidden layer, the hidden layer output. Okay, hidden layer output. So in this case, we can see here that there is the matrix dot product of hidden layer activations. So these are the hidden layer activations. Okay, so hidden layer activations, and then output that is W out. There is the weight of the output layer. So these are the weight of output layer plus of here the B out. That means bias of the output. Then we will get the output layer input. Okay, output layer input. And this output layer input we have to pass through the sigmoid function to get our output. So get our original output. So here is the this is our output. So this is our predicted output. Okay. So that means this is our end of our forward propagation. So for in forward propagation we will get up to this value. And the next what we have to do, we have to find out the errors. So that means it is we have to subtract the original subtract the predicted output from the original output. So original value is 1 and predicted is 0.79. Then find out the error. Okay, so we will get the error next. So we can see the errors we have computed. And from the error, what we have to do, we have to find the slope, that is delta of output layer. So it is the derivative of the sigmoid of output. So derivative of sigmoid of output. So output we have, so output, these are the output, or we can say these are the output. These are the output. And then if we take the derivative of this of this, then we will get the slope output layer slope. Here the output layer slope. So how can we find out the derivative? It is easy because we already know that that is uh, so this is our sigmoid values. Okay, sigmoid of sigmoid of the predicted values. Then it will be to find out the slope to take the derivative. So sigmoid of that value times 1 minus sigmoid of that value. So we will get this. Okay, output. So output slope we will get that. And now derivative of the sigmoid of hidden layer activations. So here these are the hidden layer activations. We have to take for each and every values, we have to find out the slope, or we can say delta hidden layer. So here the delta hidden layer. If you want to compute that, then uh, this is the sigmoid value. So this value, then 1 minus of again that value, we will get the derivative. So this is the derivative of the sigmoid of the hidden layer. Okay, so we got the derivatives. And now the next thing is, after getting those derivatives, we can find out that there is the delta output. So delta of output sum, or delta output. So here the error times slope of output layer. So we have already calculated the error and the slope of output layer. Here the learning rate, actually no need to use the learning rate, or consider that learning rate is 1 at this case. Okay, so it is error times slope of output layer. So error, so this is error, and we have the slope of output. So just multiply these two, then we will get the delta output. So here is the delta output. So this is a delta output sum. We have calculated the delta output sum in our sequential processing also. Okay? So after this, that after the finding out the delta output sum, we want to find out the error at hidden layer. Okay, so it is the dot product of delta output. So we have the delta output, like this is our delta output, and also we have the uh, there is weight of the output layers. So here is the weight of the output layers. So if we multiply these two, it is in the dot product. So this is two vector. This one is, and this one is also one vector. Okay, so this and dimension of this vector is, it is 3 times 1 also. Okay, so now if we want to multiply this, that is, we can see that it's not possible to multiply. So what can we do? We have to transpose one. Okay, we have to transpose one. So that's why here is the W out transpose. So that means it is transposed. So if it is transposed, then we will get 1 3. Okay, so now it is possible to uh, sorry, it is possible to multiply. So in this case, we can see here. Okay, so that means we can see here, if we transpose this one delta output, so instead of this, so here is the 3 times 1. If we transpose this one, then it will be 1 times 3. So transpose the delta output, or place this one first or this one second. So then we will get what? We will get the output of 3 times 3. Okay, 3 times 3. So that means the output of 3 times 3. So here is the error at hidden layer. It will be 3 by 3 matrix. So using error at hidden layer. Okay, so error at hidden layer we have already calculated using this. That means we have to multiply these two matrices to find out the error. Uh, then we have to find out delta hidden layer. Okay, delta hidden layer using our slope of hidden layer and error at hidden layer. So previously we have computed those, that is slope at hidden layer and error at hidden layer. Then if we multiply these two, then we will get delta hidden layer. So delta hidden layer, these are the delta hidden layers. So delta hidden layer. That means delta of age results. So we have previously computed this in our sequential processing. Here is also the same thing. Error at hidden layer and slope of hidden layer. And then from this, there is the delta hidden layer. So from the delta hidden layer, uh, now we can find out the weight of the output layer. There is updated weight of the output layer and updated weight of our hidden layer. So in case of our updated weight in output layer, see, this is the previous weight times this is the our actually the delta of hidden layer. Okay, so for the computing the delta, so here the matrix dot product, the hidden layer activations. So we know that is we have the hidden layer activation. These are the hidden layer activations, and then the delta output. So we have delta output after multiplication of this, and then this time we can apply the learning rate. Okay, so this time we can apply the learning rate, and here we have considered the learning rate is 0.1, and then we will get the W out. So this will be our new W out. Similarly, here is our so X transpose. This is our input. There is the input I. Okay, so I input and delta hidden layer. So here is the delta hidden layer. If we just perform the dot product between these two and times the learning rate. Okay, so learning rate is our 0.1. Then we will get the updated WH. Here is the updated WH. Okay, updated WH. So that means the weights are updated, output weights, and also hidden weights are also updated. Now one remaining thing here is our the updated weights of bias of hidden layer and bias of output layer. So here is this equation for, there is the sum of delta hidden layer. So here is the delta hidden layer. This is the delta hidden layer. Then we have to do the summation for those, and then uh, we have to multiply this one with the learning rate plus of the BH, the previous BH. So here is the previous BH. Then we will get the updated VH. There is bias in hidden layers. And bias of output layers, in this case, we have to apply the delta output. So this delta output, we have to sum up and then multiply with the learning rate. And then we have to add with the current, that is the output. Then we will get the bias in output units, okay. So that means these are the updated bias, so after first iteration, the forward propagation and the backward propagation, we got the updated bias and also updated weights of hidden layers, and updated bias in output layer and updated weights in output layer also. So that means we are ready for our next iteration. So if we perform the next iteration in this way, so after after maybe 1000 iterations, you will get values like this. So here we can see that the first value in this case it is 0.98, which is close to 1, and the second value here is the 0.96, it is also close to 1, and third value is 0.04, it is close to 0. So actual output we can see the actual output is 1, 1 and 0, and here the predicted output is also 1, 1 and 0. Okay, so after 1000 iteration. So this is how these steps we have to follow in our batch processing. Okay, so that means considering all the here, considering the batch size equal 3. Okay, that means you can say 3 inputs together. uh, so usually in the exam it is also given like a data set is given, a simple data set, or we can see here like the x, this x, this is given, and then you need to find out the W bias and W output and bias, the optimal W's and optimal biases. But it is not possible to calculate maybe 1000 iteration. That's why uh, usually it is asked like 1 or 2 iterations. Okay, just maybe one iteration in forward and backward propagation, or maybe maximum 2 iterations in forward and backward propagation. So from this input, I have already completed the first iteration. So try to perform the second iteration. That's just for the practice. So that's all in our today's discussion. If you have any queries or questions, or suggestions.
স্যার স্যার
Okay, so thanks all. হ্যাঁ বলো, হ্যাঁ বলো শুনছি।
স্যার ওই যে হ্যাঁ স্যার অ্যাসাইনমেন্টের কোশ্চেন নিয়ে একটু কোয়ারি ছিল স্যার।
হ্যাঁ বলো দেখি।
আচ্ছা স্যার ওই যে অ্যাসাইনমেন্টে যেটা বলছে স্যার যে কার্নেল কি ইউজ করতে অ্যান্ড হচ্ছে লিনিয়ার কি জানি বলছে মানে লিনিয়ার এসবিএম ইউজ করতে, তো স্যার এখানে কি আমাদের কোনো লিনিয়ার ট্রান্সফরমেশন দেখাইতে হবে? লিনিয়ার ট্রান্সফরমেশন স্যার, লিনিয়ার
হ্যাঁ
ট্রান্সফরমেশন
দেখাইতে
হচ্ছে
হবে।
যেটা বুঝতে পেরেছি স্যার। স্যার লিনিয়ার ট্রান্সফরমেশন হচ্ছে যে আমরা যে ইয়েগুলো পেয়েছি স্যার, ওই যে মানে 8টা যে পয়েন্টস পেয়েছি স্যার, ওই 8টা পয়েন্টসকে আগে হচ্ছে কার্নার কিকের মাধ্যমে থ্রি নিতে হবে এবং সেইটা থেকে হচ্ছে
হ্যাঁ
আমরা
হ্যাঁ
লিনিয়ার ট্রান্সফরমেশন করে বের করব, তাই তো স্যার?
হ্যাঁ হ্যাঁ এক্স্যাক্টলি। কার্নেল
ওকে স্যার।
ট্রিক
স্যার
অ্যাপ্লাই করে
হ্যাঁ
ওইগুলোকে ট্রান্সফর্ম করে একটা নতুন নতুন স্পেসে নিতে হবে। এরপর নতুন স্পেসে নেওয়ার পর এমন ভাবে নিতে হবে যেন আমরা লিনিয়ার এসভিএম অ্যাপ্লাই করতে পারি।
লিনিয়ার
কার্নেল ট্রিকটা দরকার।
ইকুয়েশন মানে লিনিয়ার ট্রান্সফরমেশন করতে পারি স্যার।
হ্যাঁ করতে পারি।
ওকে স্যার। আর স্যার লিনিয়ার ট্রান্সফরমেশনের মানে এটা এটা করার পর কি কোনো কাজ আছে, লাইক লাস্টে বলছে যে ড্র রাইট?
হ্যাঁ বাকি কাজ তো আছে লিনিয়ার এসভিএম। লিনিয়ার এসভিএম তো জানোই কিভাবে অ্যাপ্লাই করতে হয়, ঠিক না? মানে ওখানকার টার্গেট হচ্ছে তোমার আলটিমেটলি হচ্ছে তোমার হাইপারপ্লেন, যেটা হাইপারপ্লেন ইকুয়েশনটা বের করা। তো হাইপারপ্লেন ইকুয়েশন তো আমাদের ওই যে ডাব্লিউ ট্রান্সপোজ এক্স প্লাস বি যেটা আছে সেক্ষেত্রে আমাদের ডাব্লিউ ভ্যালুগুলো কি হবে, বির ভ্যালুটা কি হবে, হ্যাঁ, এবং সেটা করতে ওই যে আমরা
থ্যাংক ইউ স্যার।
ল্যাগ্রেঞ্জিয়ান ইকুয়েশন ফলো করব। ওকে, ঠিক আছে, থ্যাংক ইউ, ভালো থাকো।
ওকে স্যার।